So today I'll talk about duality. Duality is a big theme within optimization, so I'll give you the main bits of it in the time of one lecture. It already gives you a way to design new algorithms. I'll show you some of those. So like a rough overview of what I want to do. There'll be some basic convex geometry. Then we will learn whatever is Lagrange duality is, and I'll give you some examples on it. Then there is another one called Fenchel duality. Then we will look at it and we will compare it with the Lagrange duality. Then there's some results called strong duality theorems, KKT conditions, and then eventually this will give you new algorithms. So before we start with anything, what's duality? So you have some optimization problems. You're trying to minimize an objective function, okay? And you might have some constraints, etc. Almost always the problem will have a cousin called the dual. It's still going to be another optimization problem. Usually if your primal problem is minimizing something, the dual comes out as maximizing something else, okay? And if your problem satisfies certain assumptions, then these two optimization things becomes equivalent. That's the case when we say strong duality holds, like the dual and the primal gives you the exact same answer. Sometimes this doesn't happen. Sometimes the dual gives you just a lower bound for the primals. Okay, that's called weak duality. So, I didn't say anything precise yet, just what does duality even mean? This is what it means. For every problem, we will learn to construct a dual one, and the dual one will tell you something about your primal one. In the strongest case, it literally solves your primal one. So you can pick which one is easier to solve and go with that. Okay, so to get going, first fact from convex geometry, if you have two convex things, okay, and they don't intersect, then you can always separate them with a hyperplane, okay? So in the plane, if you're in 2D, you got two convex things. If they're not intersecting, you could always find the line to separate them. And this is only true because shapes are convex. If you have more complicated shapes, you may not be able to do this, okay? If you're in 3D, replace the line with a plane, higher dimensions, again, something like a plane, but more dimensions, okay? That's the first fact we would need. And how do we write this algebraically? Okay, geometrically, I see it. It's like a line or a plane or a hyperplane. Algebraically, we write it as follows. A vector A dot product X equals to B will be literally on that separating line or hyperplane. Bigger than that will be one side, less than that will be other side, okay? So one of your convex shapes, it will be included in AX less than equal to B. The other one will be included in AX greater than equal to B. A dot X literally equal to B is this hyperplane, okay? So you can always find such an A to separate them. Okay, very good. So that's the first fact we need. And now a little definition. Boundary of a convex object is closure of it, take out the interior of it. What does that mean? The red part here is the interior. Suppose if your boundary was like dotted, this was your shape, say. When you take the closure, you have everything. When you take out the interior, the boundary is the boundary, okay? Like the uttermost layer of an onion, say, okay? Does it make sense? If you have like a circle, if you have like a, okay, anyway, I think you got it. Now, what's next? If you have somebody literally on the boundary of your convex shape, okay, you could find a hyperplane touching to your convex shape literally there, and everybody in your convex shape will be on one side of that hyperplane, okay? This is called the supporting hyperplane. So you create a linear thing that separates your convex shape from everything in this side, and it is touching to your convex shape exactly on where you want it to touch, okay? Yeah, this is not a great picture. This is not convex. I agree. This is like a funky banana, right? But anyway, I think it illustrates the point. So this is what's called a supporting hyperplane. Now, using the supporting hyperplanes, for every convex shape, we attach a dual convex shape, okay? And I'll give you some examples of that. I got, say, my compact and convex shape, and you need to have the origin in your shape. If not, you can move it, of course, that's fine, okay? Then the dual of that convex shape is the collection of vectors such that you take inner product with everyone in your shape, it's gonna be less than equal to 1, okay? So you think about all the vectors that could give you kind of a supporting hyperplane. And when you dot product with stuff in your shape, you should get at most 1. Okay? I'll give you examples of this. But this is like some basic geometric thing that goes behind this duality in optimization. That's why I'm showing you that. So let's do an example. For example, if my convex shape is, say, a square, see why my pen is not willing to work today. Okay. So let's say I got the square as my convex shape, right? Now I'd like to think about vectors that gives me like a supporting hyperplane. This is a vector, this is a vector. This is such a vector. Okay? So for example, the vector, so at the end of the day, it comes out like this. These 4 vectors are literally like 4 dots, right? This is like this vector. If I write it down with coordinates, it's got 2 coordinates. It essentially comes out as like 1, 0. And, you know, if you draw that 4 of them, they give you these 4 dots, then you start thinking, the stuff here, all the vectors here, they all give me stuff too. And eventually what you get is your dual convex shape becomes literally everybody here. Okay. So the dual of a square is what's called cross polytope, or I don't know what's the name. I draw it bigger than the square, so that's misleading. I should have drawn it smaller, but I think you got the point. So that's a duality. And I should have brought that picture. So Kepler, when he was writing, what was his book? Harmonica Mundo, something like that. He was doing astronomy like 400 years ago. And the pictures he drew by hand, they include like 3D versions of this duality. Apparently he was already aware of this notion back in the day. But the pictures is mind-blowing. I cannot do them with a computer, I think. So this is ancient, basically. So let's do one more example. Let's say I got some points in Rn. Suppose these are my points. And for the moment, if you take the convex hull, you get a convex shape. But can I do like dual? What do I mean by that? Let's think about all hyperplanes you could write down with this dots. I put like 5 dots here. Here there was capital N. So the dual of this shape is going to come out, I don't know, let me be nice to myself. Let me give myself an easier shape. Okay, let me update this. If you're more artistic, you can do the shape I started off with. Let me go back to my square. Let's say I only got the 4 corners of the square. Here I got capital N many, let's say I got 4. And the dual is going to come out since in the definition, I have x times y less than or equal to 1. These dots I put are the stuff that gives me like literally equal to 1. But things that are smaller is also okay. Less than or equal to 1 is okay. So the dual of this shape comes out as a convex thing. Even when you start off without convexity, turns out this works. This is 4 dots is my set S. S perp is this convex shape. When you do one more dual, which means S dual, you end up taking the convex hull of the initial shape. Okay, so duality convexifies stuff, turns out. That's a small side. Okay, so far this is geometrically how duality looks like. Now we will try to look at it in the optimization problems more algebraically with the equation, so we can use this. Okay, so first notion of duality is called Lagrange duality. So let's set up a problem first. My problem is I'm trying to minimize this function, and it is subject to some constraints. Some of them are equality, some of them are inequalities in my constraints, okay? And then the domain of your problem is where all these functions make sense, basically intersection of all these domains. These guys, they should be all defined to make any sense. So that's the domain of your function. Now, we define the Lagrange function as follows. You take your function that you're trying to optimize. This was what we are trying to minimize. Plus, you add your inequality constraints. In front of them, you're going to allow some numbers to be put in. This lambda i's are numbers. Then you put your inequality constraints. Then you again allow some numbers to be put in next to them. So imagine you're trying to express your constraint optimization without any constraint. That's kind of what Lagrange is trying to do. It's saying, let me put all that stuff together, okay? And somehow this is going to give insight to your problem. This looks very arbitrary for the moment. Okay, then the Lagrange duality goes like this. I defined this function. Initially, I only got my x. This lambda and v are lambda I altogether, a vector lambda, vi altogether, a vector v. This I just made them up now, right? There was no lambda and v before. Okay, now the Lagrange dual goes like this. You fix any lambda and v configuration you like, then you minimize over all x in your domain. Okay, that's going to be what some people usually call this G, doesn't matter, G lambda v. Okay, so in other words, G lambda v is the infimum of this thing. When I fix these numbers, I'm trying to minimize over everything in my domain. Okay, now let's try to remember the constraints. So everybody in my domain, fi stuff is less than equal to 0. hi stuff is equal to 0, right? So in my domain, actually, these vi's don't do much. Because stuff in my domain, hix will be 0. Okay. Okay. Now, let's get back to our discussion. So suppose for a moment that you look at a x in your domain, and also suppose this lambda i's are non-negative numbers, 0 or positive. Okay. In your domain, all the hix is 0. You can ignore them. And fix were less than equal to 0. Right? They were either 0 or negative. That was the definition of our domain. Let's look at it once again. Right here, right? And if I'm multiplying a negative number with a positive number, this whole thing is a negative thing, right? So this whole thing now, this is negative, this is 0, this is some number. So this whole thing is always less than what I got here. So in other words, the expression you cooked up, even before taking the infima, this was the Lagrange function, that guy is always less than what you're trying to do on your domain, okay? And now what we're going to do is we are trying to push this Lagrange to its limit and try to see if it's going to hit the minimum of this one, which was what I was trying to figure out anyway. That's the idea of duality, okay? So let's do it a bit more precisely. So now, for any lambda that is positive, since this guy is always less than this, infimum of this guy is less than infimum of that, right? That's what I was trying to solve. And so this is true for any lambda and v you could pick. You picked one and you did this algebra mambo jumbo. You got this one, right? Now go pick the best lambda and v you could. Try to make this as big as you can. This inequality still holds because it is true for whatever lambda and v. So that means the supremum of what you could get out of this is always going to be less than equal to infimum of the thing you were trying to optimize over. So this is your primal problem. This is your dual problem. And the dual is always less than equal to primals. And when they're equal, we say there is no duality gap. They're equal to each other. You could solve this one or that one, you will get the same answer. And we'll talk about like when that happens. Okay. For now, for any problem you have in hand, if this tool looks easier to solve it. It will give you at least a benchmark, how small you could get. It will give you at least a bound. And that's also a general idea. People solve that and then they update, they solve again, dual. They try to get a very good bound, some iterative way. Okay, this is Lagrange duality, and this is usually what's called weak duality. Dual is always a lower bound for your prime. Okay, now let's do an example. So here, what am I trying to do, Jordan? I'm trying to minimize x squared such that ax equals to b. What does ax equal to b mean? It's like a linear constraint on your domain, right? All your x satisfies times the matrix A, give me b. So I'm trying to pick the minimum norm vector in a subspace that I care about, basically. Okay, ax equals to b is the measurement you picked. That's all you know. And suppose you pick the most economic one that satisfies the measurement ax equals to b. That's what the problem is talking about. Okay, now what is the Lagrange dual? This is your function that you're trying to minimize. Ax equals to b is the same thing as ax minus b equals to 0. So I'm multiplying that equality constraints with numbers v1, v2, v3. I wrote it shortly as like v dot product this vector. Okay. And then my Lagrange dual comes out as like infimum of this. In the theory we were doing before, there was a lambda and v because there was inequality and equality constraints. Here there's only equality. That's why I just got v. Okay, this is going to be that g function. And what I'm trying to do is like I'm trying to maximize this guy. Right, so let's go back. What was it? The max of that g guy is the lower bound for my primals that I'm trying to solve. And in this case, there will be actually no duality gap. So solving for g is equivalent to the other one. Okay. Now, how are you going to optimize this guy? Well, if you're trying to take the infima, that means the gradient is got to be 0. Okay. And then what do? You take the gradient, you work through. Okay, so gv, okay, let me go slow, is by definition infimum of the stuff on the right-hand side. So for which x I achieve this infimum, I don't know. The function only cares about this v, doesn't care about x. Okay, how do I find the x that gives me the minimal thing? Take the derivative, put it to 0, you find it, okay? And you figure out a better way to write gv this way. It comes out explicitly written out whatever this expression is, okay? So you literally can write explicitly what is this g function. Now, what am I going to do? The Lagrange dual will be maximizing this. I'm going to try to maximize this. It's going to be equivalent to the problem I was trying to solve. But the point is now I have no constraints. Initial problem had a constraint. The primal says minimize this, subject to that. Now the dual does not have that constraint, so it's easier to solve. Usually, not always, but usually problems without constraints are easier to solve than the ones with constraints. Okay? And then, you work through this G. And by duality, maximum of this guy is less than equal to minimum of that guy. And in this case, there will be actually equality. So you're just going to look at this function. Not too bad. There's a matrix, there's a vector. Maximize it. Again, to maximize it, take derivative with respect to v. Put that gradient vector to 0. You'll figure that out. And that will be literally your answer for this problem that looked more complicated. Yep. That's how you do this stuff in action. So far, any questions? I'll give one more example from linear programming. No dual gap means this will be not an inequality, it will be literally equality. No. The shape and its dual will be different. But when you solve the corresponding optimization problems, the number you get as an output will be the same. Okay, so the number you get from dual is always less than equal to what you get from primal. When they are equal to each other, then we say there is no gap. And this means you could either solve this problem or that problem. Okay, your initial problem could be on a cube. The dual might be on a cross polytope, but when you solve, they'll give you the same answer. Yeah. All right. So let's do one more example. Here is the linear programming example. So what is linear programming? You have a vector dot product with your x, and the constraints are a times x equals to b, and every coordinate of x should be positive. There are many ways to write linear programming. This is a way. Okay. And let's look at like the. By the way, in linear programming, there is always no gap. In linear programming, primal or dual, you can solve either. And there are even algorithms that keeps jumping. Iterates on primal, goes to dual, iterates a little bit there, keeps jumping, tries to get it faster. They're called primal dual algorithms. There's a lot of tricks you could cook up when you know duality. Okay, all right. So let's go look at duality in this setup. Here's my Lagrange dual function. So how did I write the Lagrange? This is what I'm trying to minimize, right? The function you're trying to minimize. My first constraints, the inequality ones, are like x1 bigger than equal to 0, x2 bigger than equal to 0, x3 bigger than equal to 0. All coordinates is got to be non-negative. So this is literally that constraint multiplied with a number. Okay. And then I have equality constraints as well. And they're going to come out something like that. Ax minus b equals to 0 times some vector. Okay, this is my Lagrange dual now. Okay, let's follow this through. And then you rewrite this, collect x's in one where v in another place. G lambda v will be infimum of this expression. And you work it through, it comes out as exactly this. Okay, there's not so much of a need to do algebra. It's actually simple. You can look it up later. This was your initial linear program. Okay, minimize this with respect to these constraints, and you work through this Lagrange duality. The dual comes out as follows: maximize minus b transpose times a v, such that this c here at every single coordinate is bigger than equal to a transpose times v. Okay, so this is a linear program, this is another linear program, and they will always give you the same answer. In linear programming, that's the nicest case. There is no duality gap. Now, let me talk about this a little more because this relates to many things that you might have seen before, or you may see in your future endeavors. I think I was, yeah, okay. Here is this stuff. And what I said is like there is no duality gap. Of course, it's a theorem you have to prove. Okay. And here is how you would see in textbooks. They will say duality of linear programming. If your initial was this, minimize subject to that, the dual comes out as this vector times another vector. I was doing v, here it's y. A transpose y will be bigger than c, and y is going to be non-negative. So one intuitive way to remember this is like the following. If this is satisfied, if you multiply left and right with a vector y, you would get y transpose a times x less than b y transpose, something like that. Okay. And by transpose will show up as the minimization thing. And the thing you will get from the left will show up as at least as something like that. So that's like the intuitive way I remember it usually. If not, you can always look it up, of course. But it comes out very clean. And in this case, we know when you do this minimization or this maximization, you'll get the same answer. They'll be always equal. There is no duality gap. All right. And then people will even give you recipes to do this. This is very well understood. And the recipe is, this is your variables in the beginning. You have n variables. You have a matrix M by n. And you have a vector now the vector should have m coordinates if I have m by n matrix, right? Let me write this up. And transpose is m times m, right? And this guy should also have m or n. Give me a sec. Yes, this guy should have n. I'm sorry. And then here is the maxima, here is the minima. And you just work through this, you get your dual. Here is a little more concrete example. Suppose I'm thinking about a flow through a network. My goal is to send as much flow as possible from your sink to your endpoint. I guess you guys have seen something like this in algorithms class, no? Didn't you see like max flow? Did you or not? You'd be yes or no depending on the curriculum of your particular class. Okay, so in a lot of algorithms classes, this is a standard thing, but it's from university to university, they change the curriculum. I guess here it's not standard for the moment. So the problem is this, every edge here has a capacity. Think about you're literally pushing water through pipes, okay? Or you're sending packages through your computer network, whatever it may be. And then you like to see how much you could utilize that capacity. Because let's say maybe this has huge capacity, but if this is too small, you cannot push too much through. So the question is finding the maximum flow possible. And let's formalize it. Suppose capacity of an edge from I to j is dij. And what am I trying to do? At the end, the flow is going to start from the source. I'm trying to maximize the flow I can push from that source out, essentially. And it's going to be delivered here, right? So what's that? Suppose like the flow I'm putting at from source to any node I have like 3 edges here. I'm trying to maximize the flow I put through these 3 edges. That's what I'm trying to do. That's my maximization problem. What are my constraints? The flow that is going through your pipe could be at least 0, at most the capacity. What else? If you're not source or the destination, any node in between, whatever comes in should get out, right? So that means take any node that is not source or the destination, sum up the stuff that is coming in, it should be equivalent to stuff that is coming out. So this is the stuff that comes into your node I. This is the stuff that comes out of your node I. Okay, so these are your constraints. And then you work on the dual of this problem. This is now a linear program. It's a linear objective. I'm summing up stuff. Linear constraints here, linear constraints there. This is the inequality constraints. This is the equality constraints. Okay, and you work out the dual, and dual comes out as a minimization problem. Okay, and turns out when you work it through, it also has a very nice interpretation. The dual of this, so this was max flow. Dual of this happens to be min cut. Okay, what does min cut mean? I want to disrupt this network. I want to cut some edges. And after I cut them, it will become disconnected. But I want to cut the minimum total capacity. Okay, like I want to do min cut. Let's say if I cut this too, it's going to be disconnected because this node will have no connection, right? So like you find a cut that makes it disconnected afterwards. But your goal is to find the one that is using the least amount of capacity possible. That's called the min cut. And turns out that's the dual, and it gives you the same answer as a number. Okay, so visualization, you can think about a cut like this, for example, if I'm cutting these edges. So you end up figuring out actually max flow equals to min cut. And you could design an algorithm for either one, it will solve the other one. So here we are using linear programming duality to understand this. I did not tell you details of min cut part. After that, you could either use linear programming to solve it, or once you know they're equivalent, for me, maybe for max flow, you have like a clever combinatorial trick. You don't need to do linear programming. Equality still holds, right? So there is also very discrete algorithms for this problem. This was, I think, worked out, when was it? Edmonds was a very influential scientist working for AT&T and Bell Labs back in the day. You know about this Bell Labs place? It was an industrial research lab which had so many Nobel Prize winners. Like a very, a place that helped this country so much. I hope it would be still as strong, but not that anymore. So this type of stuff was worked out there in the 60s, I think. There's beautiful algorithms. If I end up teaching algorithms class in graduate or undergrad, probably I'll teach some of those because it's hard to resist. They're very tasty. Okay, so this is linear programming duality. Let's get back. And linear programming duality, I'll give you one more exercise today. There you'll try to see the duality for shortest path problem. This time you will try to go from source to the destination through the quickest path possible. That also becomes a linear program, and it also has a dual. Okay. All right, so now let's go back to our discussion. There's a lot of stuff about this duality. Let's see how much of it I am able to tell you today. Okay, so far what we did, we defined duality. I looked through a couple of examples for linear programming duality. Now, what I defined so far was called Lagrange duality. Okay, now I'll define another notion of duality that you would see in literature quite often. It's not the Lagrange duality, it's usually called Fenchel duality. And it goes like this. You have a function that goes from Rn to Rn. At this time, you're not attaching duality to shapes, you're attaching it to functions. The dual function is defined as follows. It takes a vector y, it sends it to dot product with x minus fx. So the intuitive picture of this is, let's say if this is your f, then the dual takes a y, okay? And suppose it looks at stuff y dot x equals to something. And you look at what is the biggest difference between these two things. You're looking at y times x minus fx, how big it could get. How good of an approximation this linear vector y to your function f, basically. If I try to linearize my f, if I use this y to linearize it, how bad would it be? Okay, that's the Fenchel dual. By definition, since this guy on the right is always less than the stuff on the left, the suprema of the right is the left, right? So that means this stuff plus fx will be always bigger than this. Do you see that? It's just by definition. Why? Because move this stuff to right-hand side, x times y minus fx, it's always less than equal to this for sure. Because this guy is supreme of all that stuff. Okay, all right, very good. And then, let me kind of move through examples without explaining too much. So it turns out if you take Euclidean norm and the dual, it comes out the same thing. If you take another LP norm, like L4, L8, whatever, it gives you yet another LQ norm, turns out, where you get 1 over P plus 1 over Q equals to 1. If your P was 2, you get 1 over 2 plus 1 over 2 equals to 1, you get the same thing back. But if P was something else, it has a cousin, turns out, that is LQ norm having this property. Okay, very good. And then in general, you could take dual of any norm you like. Doesn't have to be any LP, LQ. It comes out as follows, but don't worry about it. This you will also see in literature if you're doing some more optimization, but in machine learning, you don't see it too much. This is called nuclear norm. I don't know why. Okay. So if you see it, this is what it means. It's dual of a norm with this notion. But for us, what's important is the following. Let me go. I'll give one of those examples as an exercise to save time now. These two notions are very much related to each other. That's what's important for us. Suppose I have my optimization problem, minimum of a function, such that there's an equality constraint, say linear, and there's again a linear inequality constraint. Your function could be linear or nonlinear, okay? Okay. And now I look through the Lagrange and Fenchel duality and try to see the relationship between them. How does Lagrange duality come about? infimum of the Lagrange function. I just wrote the Lagrange function on the right-hand side. F0x is what I'm trying to optimize, plus the linear constraints times a lambda, then, inequality constraints times a lambda, equality constraints times a v. And you go through algebra of this, it comes out as this, plus infimum of blah. And that infimum is the same thing as minus of supremum. And at the end, you end up getting that Fanchel duality showing up, okay? If I summarize this algebraic derivation, you end up getting this. This was your primal. Okay. Some function minimization with respect to these constraints. The Lagrange dual of this problem turns out is expressed by this Fanchel dual thing that we just saw the definition, okay? It comes out exactly like this. Pick lambda that is non-negative, multiply your b with that lambda, pick a v, and this is your Fanchel dual. So you can either pick solving the minimal one or the dual one. Knowing Fanchel dual's definition, or if it is coded up in your program you're using, allows you to write down the dual immediately. That's the main point of this. I'm not going to do too much about this Fanchel duality. Okay, that's about it. Now, now I'll talk about the strong duality case, which is when we don't have any duality gap, when the primal problem and the dual problem gives you the same answer, so you could solve any of them. When do we have strong duality, or what does that mean? Okay, so here's what does strong duality mean. Your primal was this, and you defined your Lagrange function, and you defined this g function off of it. Then we were going to maximize this. That was the dual, right? So here is the dual. When they give you the exact same answer, that's when we say there is no duality gap. All right. And immediately, if you don't have any duality gap, there are some consequences. Why? Well, because of this. Suppose they are equal to each other. And suppose the equality happens at some configuration x star, lambda star, v star. Let's say when I plug it into either right or left, I get the same number out, okay? Now let's work this through. So this is what I get when I plug that guy into my function. Let's plug the same stuff into that Lagrange thingy. What was it? You get this plus that. And there was also some HI stuff, but they're zero on the domain, so ignore them. So this expression and the thing on the left should be equal to each other. How can they be equal? This guy's got to be zero then. How could that be zero? These are zero or negative. These are zero or positive. Okay. That means as soon as this is negative, this guy's got to be zero. If this is zero, this can be any number. Okay. So this lambda i's, they pick out which f's are active on this particular location. When you plug in, so let's remember our problem domain. So here's what we got. They're either zero or less. But if they are less than zero here, this entire sum has got to be zero. How could that be? That means this guy should be killing that. I should get a zero right there. So the zero lambda i's will be picking out the constraints that are like less than zero. This is called, I don't know why, complementary slackness. Okay. So this slackness here and in lambda are complementary to each other. If you have slack here, then this guy's got to be zero. It has no slack. Okay. If you have some slack here, then this guy's got to be zero. That's why they call them complementary slacks. Right? So to have no duality gap from get-go, you have to satisfy this one. That's the first thing you realize about them. Now, like you start thinking more. When can I guarantee there is no duality gap in my problem? These are called constraint qualifications in literature. That means I'll come up with some conditions. When your problem satisfies it, then I will be sure there is no duality gap. Constraint qualification term refers to some condition that I will impose that will make sure there is no duality gap. For example, if your problem is linear programming, then you don't need any constraint qualification. There's no duality gap whatsoever. Okay? But usually your life is not as simple as linear programming. So we need to know a little bit more in what kind of problem we know primal and dual are the same, so we could solve either one. So one such thing is called Slater's condition. Let me tell you what that is. This is specifically for the convex optimization case. I have a function f0 that is a convex function. Then I have a whole bunch of inequality constraints here and some equality constraints. This inequality constraint stuff, some of them would be like linear, like affine means linear plus a number. Those linear stuff could be whatever they want. They don't have to be convex. They're just linear. And then the stuff here that is not linear should be convex. So it's like the objective is convex and the constraints are either linear or convex. And in that case, if there is any x in the domain such that for the linear stuff, it's less than equal to 0. For the convex constraints, it is less than 0. What does this mean? This guy is not on the boundary. There is something in interior of your shape. That's what it means. Not every shape has an interior. So for this condition to be satisfied, your shape should have an interior. What do I mean by not every shape has an interior? Suppose you're in 3D and you just have a line. There is no interior of a line because it's less dimensional. So as long as you got something in the interior, and if your function f was convex, you're fine. That's what this is saying. Yep. Very good. Let's do an example. Let's see which example is okay, let's work through this. This is relative entropy type stuff. This type of thing shows up whenever you're doing classification algorithms, right? If you remember logistic regression, for example, a simple example, there will be always some log type loss function in those, right? Okay, and what is my problem? I'm trying to minimize the entropy, or actually entropy is the minus of this, so I'm trying to maximize the entropy. Okay, sorry. I'm trying to maximize the entropy, and xi is the probability I'm assigning to class I. The summation should be 1, and here I put one more constraint. Previously, we worked on it without this, and we proved the maximum entropy is like 1 over n, 1 over n, 1 over n, giving them all equal weight. Now we are going to try to see if you have more restrictions on your probability assignments from the information you have about your problem. How does it look, right? Okay, so now I would like to see the Slater condition so that I can just look at the dual and solve that one as well. Let's see what is the Slater condition. I have to have somebody inside this domain. And this means looks like probably I got to have a positive thing here. That's not too bad actually, right? So it's kind of saying, don't assign 0 all over don't assign 0 to any class. That's what it is saying. I want the coordinates to be positive. And if there is any such thing in your domain, you're fine. So if you cut it so bad that when you cut it, you always get one of the coordinates 0, then you're bad. How could that be? Suppose, first imagine this shape, this one right here. Suppose it's something like this. Let me draw the 3D version. Think about 3 coordinates that are non-negative and sum up to 1. It's going to give you a triangle like this. Okay. So it will be like 1, 0, 0 here, 0, 1, 0 here, 0, 0, 1 here, and take the convex hull of those 3 dots. This is what I have so far in these 2 constraints. Then there comes the third one. Third one is cutting this. I don't know how it is cutting it. If it is cutting it only on the edge, there is no interior. That's unlucky situation. But if it is cutting it like reasonably then I'm good. Okay. So that's basically what it is saying. Right. So this ax less than equal to b it should be like a reasonable cut for duality gap to not happen. But even if it is not a reasonable cut, you can work this through. You can do tricks. If it is like on the edge, do some change of variables, try to make it less dimensional, blah, blah, blah. But you don't have it automatically, okay? Things can go crazy in the boundaries of stuff. Okay, very good. And turns out I work out the duality, and it comes out as this one. So it looks like the AX equals B constraints comes as follows. Either you can solve your primal problem, which is entropy maximization, or you can maximize this one as well, turns out. Okay, and this is not too bad to do. All right, that's a example of the Slater condition. Here's another one. This is called KKT conditions. I always forget these three people. I apologize to them. So the second K and T writes a paper in like 70s, proving what I'm just going to show you in a minute. Then someone else says, hey, there is a master's thesis of the first K, which he didn't bother to publish. He thought it's super easy, which has your theorem already 10 years ago. And then they put that name also. It's called KKT. And I wouldn't be surprised if someone else says, there was a thesis in Germany, which was in German. You didn't realize they know this, or like something in Russian. So this is kind of common knowledge. All right. So how does that go? This is my optimization problem, minimizing a function, subject to something less than equal to 0, some other stuff equal to 0. This is my Lagrangian. This G function is the infimum of it. Then I'm going to take the maximum of it. There is always like an first inf, then a max, or first a max, then an if, okay? That's always how it goes. And now my question is, do I have a duality gap or not? Are these two problems equivalent to each other or not? That's what I want to understand. And under which conditions that happens, okay? Now I'll give you a condition that holds in the case where this constraint stuff has subgradients. So we talked about subgradients already. We talked about them in the case that the stuff was convex. You don't have to have convexity for it. It gets a little trickier if you're not convex, okay? What was the subgradient? You have some vectors that behaves like a gradient for a convex function. So we talked about this. You can look up our records. So you need this stuff to have subgradients for this KKT condition. And the condition is this. 0 should be written as the subgradient stuff. Subgradients of that times a number, subgradients of that times another number, and subgradients of your stuff. So there are some vectors here, some vectors there, some vectors there. You should be able to combine them and get 0 out of it. Okay, that's the first thing. Second, in your optimal place, this should be satisfied, of course. That was part of your constraints. This was also part of your constraints. And this lambda stuff should be non-negative. And the complementary slackness we talked about. That's all, okay? And what does this KKT say? We know two things about it. If your problem has no duality gap, you have to have this stuff satisfied, okay? So this is a necessary condition for no duality gap. If you have no duality gap, if it is doing fine, this is satisfied for sure. So usually we don't know if this is true. Then what do? We check if this is satisfied. If it is not satisfied, then we know for sure there is some trouble, okay? If it is satisfied, then we look at the stuff that satisfies it, we go from there. And the second thing is, as soon as you find X star, lambda star, and V star satisfying these conditions, you know that's the optimal thing already, okay? That is true in general case. So this gives you a way to solve your complicated optimization problem. You write down the KKT conditions, then you call a numerical solver from whatever package you're using. It gives you all the assignments, X star, lambda star, and V star that satisfies these conditions. Let's say you got 100 of them. Then you write a small for loop that goes through all 100 of them and picks the best one. Okay. So that's a general thing. And then I think I have a example about this too. Let me go back to later in my notes. Yep. Yeah. Mhm. Yes. Okay. Yeah, this is a nice example. And it shows up all over the place. I am trying to minimize a quadratic function. What's a quadratic function? Usually they will give you only this matrix part. Take a matrix, multiply it with your vector from left and right. But in general, you could also have a linear part. This is a quadratic function. I'm trying to minimize it, and I got some constraints. So the problem is convex already. So I have the subgradients and stuff working out. That's not a problem. And the question is like, do I have Slater's condition satisfied or not? I only got like this constraint and nothing else. So as soon as you got somebody inside that linear space, you're fine. So for this, Slater condition is like immediate. So I know there's no duality gap. Okay. And now let's work through, since there is no duality gap, KKT condition has to be satisfied. Okay. Let's work through KKT condition and see what we get out of it. So this is my Lagrangian. And I'm trying to optimize the Lagrangian. So what do? I take the gradient. So let me remind you how this thing goes. You first define your G function as minimum Lx lambda or x in your domain. And you take maximum among all this G. That is equivalent to your dual. Okay. Now, since G is already defined as infima, I'm going to work on this at the beginning. Okay. How do I get the infima? You take the gradient. It's got to be 0. So that means this guy has got to be 0, right? And this is equivalent to say, if this whole thing is 0, this plus that will be minus C, right? Also note that X is in your domain, which was given as AX equals 0 or AX equals B, depending on how you put it. I think it was AX equals 0. Let me see. Yes. Okay, very good. And then all you need is an X and lambda that satisfies these two equations. That's all your KKT now. And you can write them down concisely as follows. Q times X plus A transpose times lambda is going to be minus C. A times X is going to be 0. And you just solve this linear equation. You solve your optimization problem. Sometimes they even call this Newton's equation or something. Okay. So it's a way to solve directly if you have a quadratic optimization on a AX equals 0 type constraint. Yeah. And as you can tell, this is probably much easier to solve than an optimization problem. You're literally solving a linear system. So that's about it. All right. Now let's circle back. So I showed you the Slater and KKT, which are constraint qualifications, which guarantees no duality gap. Now we are going to use them to design algorithms. How it is going to go. So quick reminder. This is your primal. This is your dual. And we figured dual can be also written using this differential duality. And now suppose I know the Slater or KKT. I know there's no duality gap. I'm going to exploit it to design an algorithm. This is called, one of them is called dual ascent algorithm, like gradient ascent, but using duality. How does that go? You first go pick a Y, okay? So, or lambda, depending on how you write it. I got X as my primal parameter, right? I'm trying to minimize the function F. And I have some constraints, which is A times X equals to B. That's my problem. Now, when I do Lagrangian, I got one more variable. And I got this Lagrange dual, okay? You go pick somewhere to start. And then you minimize according to X. And you'll keep iterating. That's the main idea, okay? Minimize according to X, then do the other one, keep iterating. Let's see how this goes more precisely. So that's what I want to do. And to get this, I have to have the gradient equals to that. And since you know your y, that's where you started off, you can try to take this and solve for x and keep iterating between x and y, if you can. And the algorithm then looks like this. Pick a y, minimize for x, that's your next x. Put that x back in, do a gradient ascent, that's your next y, go back, do it again, keep iterating until you converge. Why do you know this is going to work? Because you know there's no duality gap. You're going to hit that sweet spot where primal and dual are equal to each other. You're increasing your dual problem. Max of the dual is the same thing as mean of the primal. Yeah. So that's a standard dual algorithm. And there are a ton of variations of this. Okay. And they are used all the time. It's not just something theoretical. A lot of them are quite practical too. I'll show you two variants that you'll likely see very often. Okay. This idea, two particular variants. First one is called augmented Lagrangian. For some, this is essentially the regularization in machine learning. Augmented Lagrangian, I think, was out there before regularization was so commonly used. It's more or less the same idea. So you want to minimize this guy, subject to this one. You put that inside the Lagrangian, and they call it augmented Lagrangian. It's as if this is my constraint, AX should be equal to B. And don't push it so much, just penalize it. That's kind of the idea. You don't have to push AX equal to B, but if AX is not equal to B, put a penalization there and try to solve it. Okay. And there, the algorithm I just showed you in the previous page comes out exactly like this. Argmin at your current y, that's your next x, plug that in. This is your gradient, if you do the gradients there. That's your next y, keep pushing until it converges. This is implemented in whatever package you're using almost all the time. Augmented Lagrangian. And it is fairly general because, as you see, there isn't so much specification on the F. Okay. All right. So that's our, and there is even a theorem you could prove. Don't worry about it. Another thing that you will see very often is called ADMM. Let me write it up. ADMM. This also shows up in a whole bunch of problems. What is it? This time I have two functions. They are talking to different variables. F is talking to X variables, G is talking to Z variables. And I have a combination of those. The loss functions, for example, come up this way. And the constraints are again linear in X, linear in Z, and there's a vector right here. Okay. And then what do? You're going to execute the exact same idea. Write down the augmented Lagrangian in this case. But the point is, since X and Z are kind of independent in the problem setup, you exploit that. You first pick a Z and a Y. You do that argmin thing, find your next X. Then you plug it in there. This time you fix Y and X, and you do argmin on Z. That's your next Z. And then put your next X and next Z inside your gradient to update your Y. Okay. They call it alternating ADMM because you're alternating between X and Z. And this silly looking thing is so useful that I am always surprised. Okay, so keep this in mind. This could save you in some problem someday. So it first looked to me like, okay, I have an A linear, B linear, so what the heck? But then by experience, I learned if you use this carefully, it can solve a lot of interesting problems. Okay. All right. These are two standard things you would see to exploit this duality idea, augmented Lagrangian ADMM. Okay. And I'll tell you a little more, and that will be end of the lecture. So we have about 12, 13 minutes. I think I'll manage. No. Yeah, 12 minutes. I'll manage a good chunk of what I wanted to do. All right. The next thing I want to tell you about is this thing called, but let me take a pause. Any questions so far? What did we do today? We introduced Lagrangian duality, Fenchel duality. We talked about their relationship. Then we talked about when do you have no duality gap, Slater condition, somebody inside for convex case, KKT condition in general, as long as you get a subgradient. Then I showed you some linear programming duality stuff, this graph type things that I think is nice. I also showed the quadratic optimization through KKT, which just became linear when you look at the dual. And then after that, I started talking about this dual type algorithms, dual ascent. And we showed two specific cases of that, augmented Lagrangian and this ADMM. I think that's about it, right? That's so far what we have done. And now I'll show you one more algorithm or general algorithmic idea. And that's all I think you need to know as the core ideas of this duality. Duality itself is a thing. People who studies optimization theory maybe does a lot more than what I show you today. But I think this is good enough knowledge to know your basics and exploit them when you're actually trying to solve a problem computationally. I'm not claiming I showed you everything there is about duality, but I think these are the core stuff, okay? Okay, now let me show you the last algorithm that I wanted to show. These are called usually bundle methods for regularized risk minimization, but the name is too fancy. Basically, you get a situation that you have in machine learning and you're gonna try to use this duality type ideas to come up with an algorithm, okay? So how does it go? You have a loss function. You have, say, m data points. You sum it, you average it. That's your reward or loss. And then on top of it, since you're doing machine learning, you put some regularizer. And then on top of it, you put a parameter. This is like L1 norm, L2 norm, entropy, whatever regularization you're using. And this is our typical situation in machine learning. We got some data. These are those xi's. We are trying to find the best parameters for our models. Okay. All right. And this will go use subgradients. You don't have to have a derivative. As long as you can have subgradients, the idea works out. So what is the idea? This RW, if I pick another W perp and the subgradient of that vector, by definition, I have this. I'm trying to minimize this guy, right? All right. And I know even in the minimum case, I have this lower bound. So it's got to be useful. Even if this was the optimal assignment, this is still true. Okay. So we're going to try to utilize this to get an idea on how small this guy could be. That's the idea of this stuff. Let me show you step by step. So you pick a lot of kind of vectors in an almost random way. Only thing you need to do for every vector you picked, you need to be able to pick a subgradient. Okay. Then what's next? You look up all the lower bounds that you could get out of them. So this here, plug in the vector you sampled and the subgradient you created. And this all are less than equal to what you're trying to do. Okay. Or what you were before in the iteration, say. Look at all of them together and try to pick the biggest one among them. Okay. So they call the biggest one, if you sampled T of them, RTW. And since all of these guys are less than this, of course, the maximum is also less than that. So you are trying to get a decent lower bound for how small you could make this guy by like sampling a whole bunch of vectors and creating subgradients and writing that inequality. Okay. Now, how does this go? So this is your objective. And when you do this T step, so without this T, this was the objective, the loss regularizer times lambda. But here the point is, when I sample a parameter and I plug it into the loss function, that's literally a number. Okay. So when you're trying to go through here, the only parameter remaining is this guy. Okay. All right. So what do? You write this up and you try to iterate. And how does the iteration go? Let me try to, wrap this up. So this is the thing you defined. You just sampled a whole bunch of stuff and then created subgradients and wrote inequalities off of them and go pick the biggest one among those. This was like arg max of stuff, and it comes out as follows. And then you could write down the stuff up there, which was written this way, in a little bit nicer way, because this is a vector you sampled, it's the subgradient you created. When you dot product them, it's a number and you know that number. So this is the thing you can change. Okay, so if you write it that way, so this is a number, this is another number, let's call it BI, your thing comes out as follows. This is your primal problem in this setup. And you work out the dual. Apparently it comes out this way. And then you solve the dual, you do that dual ascent, and you try to solve your machine learning optimization problem this way. Okay. This is again a general collection of methods. It's called bundle methods for regularized risk minimization. If you want to Google and find out the libraries and papers about this, this is the buzzword you need to Google. It's not that commonly used because people tend to assume they have derivatives, so they don't have to use subgradients and this kind of trickery. But it's not always the case. So the papers who work on this kind of algorithms, they always have very good examples that are practical. But somehow it still is not so much mainstream. I don't see this used as often as, say, ADMM or other stuff. So, but it is good to know, since we developed all the machinery. We developed subgradients, we developed duality today. And I think this is good enough. That's all I wanted to say about duality and algorithms that is coming off of that. And this is also the end of our optimization discussion in this course. I will probably start talking from Markov chain Monte Carlo in Thursday. I'm still undecided on the precise order. I'll decide it today or tomorrow. Any questions about optimization in general before we close the topic? We have about 3 minutes or so. Okay. So as a summary, we started off with unconstrained optimization stuff: gradient descent, stochastic gradient descent, coordinate descent. We also talked about some convex constraint techniques. If you remember, this projected gradient descent, or this thing called Frank-Wolf. Then we started talking about non-smooth functions, the stuff that you don't have the gradient. Then after that, we talked about proximal point type algorithms. And then we talked about duality and the dual algorithms today. And I think it's a good place to wrap up this discussion. So thank you so much.